In this video, we're going to do a little primer on NumPy, and notably a very important object inside NumPy, the NumPy n-dimensional array. Now, there are many ways to make collections of objects in Python, right? And a very simple one is a list. But in Python, you can put many different objects inside this kind of collection. You can have, for example, here, integers, floating point numbers, some forms of irrational numbers which are still floating point, but also strings, Boolean objects, and basically any kind of Python object you can think of. Now this is okay, of course, and great for many things, but if you actually want to work with a lot of data, that means that the interpreter has to go through each object and check what it is. And on very long lists or collections, this can be a very large overhead and make your computation much slower. So in scientific Python, we prefer to use a very specific kind of collection, which is called a vector. Now, what's the difference between a vector and a general Python collection? It's that a vector contains exactly one data type. It can have a lot of items in it, but they must all have exactly one data type. So for example, here, if you create a NumPy array with an integer and a floating point number, well, the result you're going to get is it's going to be converted here. NumPy chose float 64 because that was what worked well to be able to represent both these numbers. And so it converted the integer 1 to the floating point number 1. And you get a vector with exactly one type for everyone, which is float 64. Now, there are many types inside NumPy. Most of them that we'll see together are for integers and floating point numbers. It also supports complex numbers and then some very specific types. And then there's the case of the unsigned integers, which is a special case in computer science, and we'll talk a little bit about it. So what's a very simple representation? For example, let's take a uint 8. 8 means 8 bits, so 1 byte of data. So if you represent numbers as on 8 bits, then you get here 8 zeros or ones, okay, 8 bits. And so you can represent numbers from 0 to 255, which is when you put them all to 1. So 1 byte, 8 bits of data. Now, U is for unsigned, because here we're representing only positive numbers. With an int 8, you would go from -128 to +127. So in practice, when you create a NumPy array, if you specify the type, so here I'm specifying the type uint 8, and I create an array with 8 values here from 0 to 7, well, what's actually happening in memory, okay, your computer has RAM, which with a lot of zeros and ones, which are all addressed as bytes. So here I'm requesting 8 values of 1 byte each. So if I ask for the Python object A to give me its attribute n bytes, then I'm going to get 8 values, which you see here, starting from 0 and then going all the way up to 7, sorry. So the item size here is 1, it's expressed in bytes, and you can also get this from the object. It's saying my D type is uint 8, so every object inside the vector is going to take up exactly 1 byte. Now I could also, for example, make another vector where I only put 2 values, here 0 and 1, but I'm asking for another type, which is uint 32. So 32 bits is 4 times 8, it's 4 bytes. So what I get in memory here is an item size of 4, okay, so 0 is stored on 4 bytes, and then 1 is again stored on 4 bytes. So notice that this array also has an n bytes of 8. It has 8 bytes to represent data, but it only has 2 values because each one is represented on 4 bytes, here and here. Now, 0 is all zeros, that's pretty easy. You might be a little surprised by 1 to see that there's 1 on this side. That's not how a normal binary number would be written. You would write it with all zeros and a 1 at the end. So what's happening here is this is what we call little endian, and numbers on computers can be represented one way or the other, little or big endian, and very often they're little endian with NumPy on modern systems today. But you don't have to see this in practice, of course, every day. However, this does mean that depending on the type that you choose, well, you can have much bigger arrays for the same amount of data. Here, you take up the same amount of memory for 2 arrays that have very different quantities of data. Okay, so going back to our array, I'll make one a little larger this time. I'll take 9 values, and I'm going to show you why. It's because, as I said, NumPy has n-dimensional arrays, so you can make other things than just one-dimensional vectors. You can make, for example, matrices. So 8 wouldn't be very practical for a square matrix, but I'm building here a 3 by 3 matrix with this 9 valued one. So how do I do this? Well, I define a new matrix B, which is a simple reshape of A. Okay, so first this A that you see up here has 9 values directly, and then B reshapes it to 3 by 3. Except something weird is going on here, because the RAM in your computer cannot support 2D information. Okay, it's just a very long string of addressed data. So it's 1D. So how do you fit a 2D matrix in this 1D RAM? Well, because it doesn't work directly, what NumPy does is that first when you create A, it allocates these 9 slots here of memory to store this one-dimensional vector that you see on top. And then when you ask to reshape it, what NumPy does is that actually creates this new object B, which is a pointer to A with some, let's say, decorations. B has an attribute base, which will actually evaluate to true if you ask if it is A. So it knows that A is its base, but it also knows that it has a shape, which is 3 by 3, and so also a number of dimensions, in this case 2. B in this case is called a view of A. There's no way to actually create a two-dimensional array in the memory, but so you create a one-dimensional array A, and then you create a view on this array, which tells you how you should interpret it and how many dimensions it's supposed to have and how you should address it if you want to access it. So this has some implications for you as a NumPy user. For example, let's say that here, this syntax B bracket colon means that I'm selecting all the elements of B and putting them to 0. Okay, so now B points to this 3 by 3 matrix, which is only zeros. But there is only one matrix in memory here for everything we did, right? There is actually only one area of memory with 9 values addressed by A, and then B is a view of that. So when I change the values of B, I might wonder what happens to A. In Python, if you create 2 different objects, you change one, usually you don't expect the other to be affected. But in NumPy, this isn't true. We're only pointing to a single place in memory. There are 9 slots reserved for what we're doing here, and so changing B also changes A. So what do I do if I actually do want to create a separate version, a copy of A, where maybe I want to change things without it changing A? Well, there are several things that do that, several methods that lead to a copy in NumPy. One way, for example, of doing it is starting from the same array A, and then creating a new array B, where you will say, okay, B is A of A larger than 0. This is something you can do. I'm filtering out the values of A that are actually larger or equal to 0. It so happens that in this case, that's true for all the values of A. So I'm going to get all the values of A going back to B. But NumPy doesn't know that a priori. Maybe there could be some negative values in your array or things that are outside the scope of the mask you're using. So, of the conditions, sorry, you're using. So in this case, well, it is exactly the same size, but it could be any size. And so that would be much too complicated to have a view of A that is actually something that is only parts of A. So in this case, NumPy implicitly copies A first and then selects the elements and puts them in B. So B in this case is not a view, it's a copy of A, and so changing B would not change A. So in practice, in memory, you have allocated twice 2 different spots of 9 bytes in memory to do this. This also means that if you ask for b.base is A, you will get false. b.base is actually none, because B is not a view anymore, it is a full-on array. So this can be quite confusing when you're getting into NumPy. When do I get a copy? When do I get a view on the object I'm trying to manipulate? And indeed, that's the central point that you need to get into when you're starting out with NumPy. And there are basically these 2 outputs possible, view and copy. And one way you can think about it that works many times is that any type of direct indexing gives you a view. So indexing can be getting all the values of A, or just selecting as a fraction of it here from indices 2 to 5, or here extracting the 3rd column, or just reversing the entire array. All of these can pretty simply in memory be expressed as a view of A, and so they all return a view of A and not of copy. Notably, it's also true we used reshape earlier. We saw that that's also a view, and the special function ravel, which will always make your array completely flat, also returns a view. When do you get a copy? Well, we saw that if you use a condition here, which is called masking, so I basically build a vector that says which values I keep and which I don't, and this is what I give to A, then I'm going to get a mask and a copy, of course, sorry, of A. It's also true if you use a list of indices that you want to keep. So if you see here, there are two brackets, which means I'm actually inserting a list here as argument for the brackets of A. And so again, because I can select any indices, even some of them several times, well, there's no way to express this as a view, so it's going to be a copy. There's also, if you want to be sure that you're copying an array, the method a.copy, right? And note that flatten is the same as ravel, but it makes a copy. So there are some general rules, but it can also be quite confusing. So in essence, if you're not sure about what's happening in your code and you're wondering if you are making a new allocation or not, you can check by simply printing the a.base value. If it's none, you know that you're looking at a base array, a true array, and so there's no other array that it's referencing. But if it's not none, then you are viewing another array. And you can also test if it is equal to another array, if they have the same base, to see if they're actually changing the same memory or not. All right, that's all for this video, and I think you really need to practice if you want to get acquainted with these mechanics and become efficient while using NumPy for scientific Python. Thank you.